Howdy everyone, Mr. Reed here. Going to get to talk about optimization today. Optimization is one of my favorite parts of the calculus course because it's actually a fairly simple calculus idea, but you get a large variety of problems that you can do optimization on, and it's the setup or the problem solving that goes into it before you do the calculus that ends up being the interesting part, which I think is kind of fun. So, optimization, a fancy word for getting a value to be as small as it possibly can or as large as it possibly can. This should sound really familiar because we just came from graphing. And when you do graphing, you are trying to find, as part of the entire process, local minimums and local maximums. And you may have even commented on absolute minimums and absolute maximums. As you do that, look for those absolute minimums and maximums. You have to test critical points as well as boundary conditions. So if you can imagine that we are a box making company and our one and only goal for right now is to minimize the cost of making a box of a certain size. And we are told we have to use certain materials, and so that's kind of our parameters. So what do we want to do? Well, if we want to minimize the cost, then we have to think about how we are going to come up with an equation that will allow us to describe that cost in terms of other things that we can measure or know. Once we have done that, we also have to consider that there may be boundary conditions. For instance, I probably can't use negative amounts of material. That doesn't really make a whole lot of sense. So there are going to be some end conditions that I need to consider. Maybe if you don't use any plastic or something like that, that will have to work into the problem as well, not just the critical points. So that's basically the idea of it. It's basically a graphing problem without graphing. But the setup of getting that equation that you're going to work with in the first place is the interesting part for most of these. So the textbook describes something similar to this anyway, as a list of things that you can do in order to set up an optimization problem. First one's pretty self-explanatory and kind of weird that you put that down, but understand the problem. So what I mean by that is, like I was just saying with the box example, you need to be able to describe to yourself mostly, but other people would be fine too, be able to describe in words what it is that you're trying to find. So if your goal is to find out the smallest cost that you can have for making these particular types of boxes, then if you can say that and you understand what that means, oh, I'm looking to minimize the cost of these boxes, then you get the drive of the problem. You understand it. Now, 2 and 3 together are probably the nastier part of the problem. 2 mostly. So 2 is all about taking what you understand and giving some mathematical context to it. So if there's Pythagorean theorem there, you probably set something up using that. If instead it is some sort of volume equation, then you go with that and kind of tweak it a little bit. You are looking for mathematical models that will help you to represent the situation you're trying to discover or describe from part 1. Now, once you have got some sort of model going on, you need to break that model down into the thing that you're trying to minimize or maximize. That's going to be a single variable. So you want that thing to be isolated, and then everything else is to be described using a single variable only. Because if it is, I guess if you can think about it as a 2D graph, the ones that we're used to seeing, you will have usually your dependent variable is the one that you're looking to optimize. And so you're looking for maxes or mins, so your y values being highest or lowest that you can possibly imagine. And then on your other axis, your independent variable is going to be there. Well, what would happen if you had 2 independent variables? Well, then you'd need like a 3-dimensional graph in order to show what was going on there. And that, looking for mins and maxes on that is obviously going to be possible, but it's going to be very different compared to what we're used to looking at. So we want to, for sure, describe things as a single variable only. So just be aware that that's the process that we're going to take and what we're going to try to do to set this up. Writing the domain of the function is important because recognizing where endpoints might be. Because like we saw with the graphing, just because something's a local min or max doesn't mean it's the actual smallest or largest possible value that you could have. So you have to kind of like test around the end conditions, because it might have started lower even if it wasn't a slope was 0 there, or might have started higher, etc. All right, and then when you're done, you'll have to sometimes, most of the time, you're going to have to take a look at the solution and kind of understand what that means. And so we'll see that with some examples. So most of what I'm going to do right now is run through several examples because I like this stuff, and I'm going to just give you some, I guess, seeing me solve some of them. If you want to pause as we're doing it and you want to give it a go and then just see what I did, we should get the same answer in the end, even if our steps are a little bit different, but you can follow along and see how things go. I'm going to start off conceptually very simple. So this says find two integers whose difference is 100 and whose product is a minimum. Now, the integer part is actually really hard to define. I'm going to do it for real numbers and just see if it ends up giving me integer answers. If it didn't, we'd have to fish around a little more to kind of get an idea what's going on, but I know that this one's going to end up being okay. So find two integers whose difference is 100 and whose product is a minimum. I'm going to say my two integers, hopefully they're integers, x and y. So I'm going to say that their difference, it doesn't really matter which one's larger. So I'm going to say x minus y is 100. And I'm also going to say that their product, x, y, is a minimum. So I'm going to say xy is the quantity that I'm looking to optimize. So I'm going to call it Q for the time being. Could name it P for product. It's totally up to you. I can't remember if it's this textbook or not. They use Q fairly frequently. I usually don't, but I was having a brain cramp, so I went with the Q. I probably would put P normally for myself. Probably capital P. So next up, I'm going to say that this is great, except for the quantity that I want to optimize. I want this to be a minimum. Has to be written in terms of a single variable. Right now it's x and y. I'm going to write it in just y. Now, that would be y times, and then whatever my x value is. Now, my x value, can be rearranged from this top equation to be stated as 100 plus y. So I'm going to get 100 plus y is that x value. So this one is x, and then this one's obviously y. So that means that my quantity is now described in terms of only a single variable. I could have selected x's instead, and maybe I'll show you that in just a moment. But that here we go. This is quantity described in terms of a single variable. Now, I don't necessarily have to multiply that out, but I'm going to. Now, we want to optimize this. So we want the smallest or largest, but in this case, smallest possible value for this product. So we're going to take the derivative with respect to y, because as I said earlier, when you're thinking about graphing, I basically have q along this axis and I have y along this axis. So as I'm going out along the y, I'm trying to find out where my q is actually a minimum. So we want to take the variable with respect to the independent variable. In this case, it's the y. So just a straight up y derivative, which is going to give me 100 plus 2y. This, I'm kind of glad in a way that I picked the y, because a lot of times we see y's and we're like, oh, it's implicit. because we're taking x derivatives of things that have y in them. This is the variable that it's written in is y, so I'm taking the derivative with respect to that variable because I just want to know where q is the biggest or smallest. In this, I'm kind of changing y and seeing what happens to q. So what I actually want to do is it's dq by dy, not just q. So dq by dy is equal to 100 plus 2y. I could probably call it q prime, and that would be fine. And I am interested where this thing is equal to 0. It doesn't have any does not exist, and we'll probably see that that's pretty common in terms of like places that we're actually interested in. But we can solve this by switching that over and saying that y then is equal to negative 50. So if my y is equal to negative 50, I can go back up to my x being 100 plus y, and it's going to be 100 then plus negative 50, so my x value is 50. So we could kind of test that really easily just to make sure it fits the conditions that we started with. The difference between them, 50 minus negative 50, is 100. That's good. And the product is 50 times negative 50, which is negative 2,500. That's a pretty small number. And we could kind of say, well, what would another example be? Like 100 minus 0, and 100 times 0, is just 0. So that's not even close to being as small as negative 2,500. So, that seems pretty reasonable. I'll show you what that looks like graphically. So I'm going to do iPad and graph, I guess. So let's go ahead and if we've set up that quantity properly in the first place, now I'm going to mess things all up in terms of the actual variables we're using. I'm going to say y is equal to x times x, or 100, I guess, plus x. So this graphically is basically what we're dealing with here. Now it has this parabola shape because obviously it is a parabola. The location of the vertex is, of course, we said negative 2,500, so I should be able to scale my graph appropriately to see if that's actually true. It looks really good. So this is the function that we were doing. It was only a parabola. We didn't need calculus, actually. We could have found that vertex by doing like make negative b over 2a or something like that, and then finding out what the y value or the quantities value would have been there. So that would have been pretty straightforward. Now, I don't know if I should do this and kind of overkill it a little bit, but if we had selected originally a little bit of a different path, and we had said, oh, I think I want to describe the quantity in terms of x's instead. So my y, if I move that over, would actually be x minus 100. So you'll notice that there's a little bit of a difference there. It's 100 plus y versus x minus 100. So in this case, my quantity would be x squared minus 100x. If I take the derivative there, set it equal to 0, I'm just going to be kind of sloppy and not write as much down there. Be 2x minus 100. Move the 100 over, divide by 2, and we get x is equal to 50. You'll notice that instead of getting the minus 50, I get the 50, but that's because up here, when I'm saying that x minus y is equal to, whoa, that was awful, x minus y is equal to 100, I've kind of picked my x to be the larger one because I get a positive difference when I subtract y away from x. So anyway, it just sets up the same way. I get my x first and then I put it back in to be able to figure out what my y is. And so it didn't matter whether I chose y as my variable or whether I chose x as my variable. As long as we take the derivative with respect to the single variable that we've set it up with respect to, we are good. All right, let's go back to this and try another one. Okay, so here's a box. So a box with a square base and an open top must have a volume of 4,000 cubic centimeters. All right, find the dimensions of the box that minimizes the amount of material used. Okay, so I know that this is a square base box. So I'm going to draw a little diagram. So I'm not very good at this, but that's all right. So x and x. I don't know that it is a cube, so I am going to say that this is h. I also know that there is no top on my box. So I have my four sides that are all going to be the same size, and I have my base that it sits on that is a different size. So can I describe those sizes? So I have 1 x squared, and then I have 4 xh in terms of the number and types of sides that I'm working with here. So I do know that my volume, which is x squared h, is supposed to be 4,000. I'm not going to put the units in there. I'm just going to say that x is measured in centimeters, and so is h, so everything would work out unit-wise, and that's good. All right, so that's one thing. Minimizing the amount of material used would be surface area. So my material used, I'm going to call it A for surface area. That would be equal to the x squared plus 4xh. So all those sides just added together, their areas. All right, so that's good. This is the quantity that I'm looking to optimize, the area. Now, right now it's written in terms of both x and h, and that's a bad thing. So I need to get rid of either the x's, which they're in 2 spots, or I need to get rid of the h. I'm going to I think it's going to make it look algebraically a little simpler if I substitute that h out. And the way that I'm going to do that is I'm going to take that other piece of information that we were given in the problem, that the volume was equal to x squared h. X squared h, that volume is equal to 4,000. So I can say then that the h is equal to 4,000 divided by x squared. So that 4,000 divided by x squared is another way to say h, because of that volume restriction that we have. So I'm going to rewrite my area as being x squared plus 4x and then h. So 4,000 over x squared. All right, so now I do have an equation that describes my area only in terms of one variable. So that's the x variable. H is it's built in there still, because that's how we got that second term there, the 16,000 divided by x. But it's not, we've expressed it so that if we change just x right now, we can see what the effect is on that area. All right, so we want to take the derivative of this and set it equal to 0 to look for critical points. So I'm going to just call it a prime, and so that's my derivative. It's with respect to x, so I get 2x, and then minus 16,000 over x squared. So that's the way that I'm doing that mentally, is I'm thinking that this is the same thing as an x to the minus 1. The negative 1 comes down, switches the sign from positive to negative, and now it's to the power negative 2, which I stuff back into the denominator and get something like that expression that I wrote down below. All right, so we want to take that and we want to set it equal to 0. So that's 2x minus 16, not what I meant. 2x is equal to 16,000 divided by x squared. I'll multiply that x squared up onto the other side. Now, as I do that, it's kind of getting rid of the fact that we can't, in this particular case, have an x value of 0. But obviously x can't be 0, because if we were to find that x was 0, that's going to be really awkward, because we have to have a volume of 4,000, and you can't really do that with a square base that has no dimension to it. So that doesn't really matter there. I'm going to multiply that x squared up onto the other side, get my x cubed, and divide both sides by 2 and get 8,000. So in this case, we get x is equal to the cube root of 8,000. I believe that's 20. And so we would say that if our x was 20 centimeters, we are going to get either a local max or a local min. Now, last time I didn't actually check what it was that I got. I'm going to this time. I'm going to use a first derivative test and just show you what that would look like. So this is going to be the surface area, we found that at 20, there is kind of a critical value. So I'm going to test the derivative, which is this part right here. I'm going to test it before we get to 20 and after we get to 20. So if I were to put in 1, for instance, that would be 2 minus 16,000. That's very negative. So it's the first derivative test on this interval before we get to 20 is negative. If I do the same thing after 20, so I take like 30 for instance, that would be 2 times 30 is 60 minus, and we got to just test to see if this is going to be bigger than 60 or not. So it's going to be, as I said, 30. So 16,000 divided by 900. 160 divided by 9. So that's going to be less than 20. So that, because it's less than 20, it's definitely less than 60. So we would have a positive. So we'll get positive on this interval here. And so we have described, because it is negative and then positive for those derivatives, this is definitely a local min. And since it's going down, I guess if we were to kind of go this way and say, well, there's some sort of boundary there, but 0 doesn't even make sense. Because there's no switching of what's going on there, and we want to find the local minimum, and it's decreasing everywhere from there, we're not going to have anything that we need to find out that end, because it basically starts way up here and it just goes down, 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 down until you get to 20, and we care about that low point. So on the other side, it's just up, 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 and it doesn't even matter where it ends because it never kind of cuts back down. So that definitely is our absolute minimum. So we have a minimum material used box when our x is equal to 20 centimeters and our h then is equal to, and h is described as being 4,000 divided by 20 squared. So 20 squared is 400, so that would be an h of 10. So we would have a 20 by 20 by 10 box would be the minimum amount of material used in order to get that 4,000 cubic centimeter box. So that's basically that. I can, again, just because it's not a bad idea to take a look at this and get kind of an idea that it seems to be going okay. I'm going to go to, I'm trying to figure out which one I want to put. All right, here we go. So what I wanted to describe, I guess, is the equation that we had right there. That surface area one, that is, I guess this is probably the nicest looking version of it that's in a single variable. So that would be y is equal to x squared plus 16,000 over x. Now, we are expecting the answer to this to be $20. I don't know, I'm mumbling to myself. 20 for the x value. Now, there it is. I didn't actually at any point in time. Oh, never mind. I didn't figure out what the surface area was, so I was kind of just skimming along for it as I zoomed out. We could have found out what that minimum surface area was, and then I'd have a much better idea of where I should be looking on that graph. I didn't. That's okay. And so that x value of 20 does seem to correspond here with a local minimum. Now, obviously something funky is going on the negative side of things there. And so it does have a vertical asymptote that would be occurring at 0. As we said before, we don't care what's going on the negative side of things there. So we don't really have to explore what's going on that side. So we found that single critical number over here, and happy with how that panned out. Technically, on the other side, it comes down from negative infinity, but again, that doesn't give a realistic parameter for the problem. We don't care about the size of this box when the square base has a negative 0.001 centimeter dimension times another negative 0.001 dimension. It just doesn't make any sense. So that's that one. I think I might do maybe one more for now, and maybe I'll do a couple more examples on Wednesday or a little bit later this week. Let's see here. I like this one. This one's fun. So a rectangle is inscribed with its base on the x-axis and its upper corners on the parabola. Y is equal to 9 minus x squared. So it kind of looks like this. This is easiest to show using some quick little sketch. So if this was 9 for the y-intercept, then it would be plus or minus 3 would be our x-intercepts. So what did I do there? So I guess it would be, if I kept the scaling pretty similar, kind of like that. So if I read it again, rectangle is inscribed, that means placed in, drawn inside, with its base on the x-axis. So we have something down here, and then its upper corners touch the parabola, kind of like this. Now, I'm going to change my color up, and I'm going to show you what it would, that there's more than one example of a rectangle that would fit under there. And so there are, well, an infinite number of rectangles that could fit under there. You probably, the first one that I drew out of that bunch, visually it looks like it's going to have the largest area of the trio that I drew. Of course, there's some, obviously it's not any exact thing. It could be just a little bit bigger or smaller than the one that I drew, and that would be fine. But what we're trying to do is find that largest area rectangle that we can fit between the x-axis and that upside down parabola. So the thing that we're looking to maximize is area, and I need to probably label some parts of my graph so that I can understand what's going on. So this point, if I say that it comes over as far as x, where the edge of that rectangle is, x because it's a variable, I want to be able to put it at different spots along there. So it'll be at x comma, and it goes up as high as hitting the parabola. How high is the parabola? It depends on the x value, but that parabola's y value is actually already in the question described in terms of x. So we're given, as part of this parabola, or this word problem, it tells us 9 minus x squared is the y value of that parabola. So that means that's the y value of that coordinate, the point that touches on the corner of that rectangle. So we get x comma 9 minus x squared. Excellent. So how do we use that in order to describe the area of the rectangle? So the area is going to be equal to, it's actually not just x, because this thing's symmetrical, so it goes to the right and it goes to the left as well. Because the parabola is symmetrical around the y-axis, you can assume that if something goes up to the same height on both sides, it's the same distance away. So it's going to be 2x, because there's an x here and there's an x here. So the entire width all the way across is going to be 2x in terms of the way that I have labeled it. Now, we could label it differently, but I'm pretty comfortable with that. So 2x across the bottom. Next up, the height is going to be the y value of that corner, which is 9 minus x squared. So if it's 2x all the way across the bottom, that means the x value is how far you are from the origin to the right. And then you can use that as the x value for your point that sits up in the top corner. And so you would get that the y value there has to be 9 minus x squared. So we have an equation for area, and it's now done in terms of a single variable. So, excuse me, choking on my spit. The area is equal to 18x minus 2x cubed. So I'll just multiply that out. Gives us a really tidy looking derivative to take. So a prime is equal to 18 minus 6x squared. So that means, I'm going to look for critical numbers, so I'm going to set that equal to 0. So 18 is equal to 6x squared, which means that 3 is equal to x squared, or x is equal to plus or minus square root of 3. Now, I think I'm going to define my x as meaning how far out to the right I am. Now, you might be able to say, because, if you just call it negative, just means the x, oh good gracious, sorry, it means the x that you are looking at is out to the left instead of out to the right. I think that that's not really that important or care about that all that much. So I'm going to just say that we found that it's positive root 3. And I'm going to say x values that are smaller than 0 don't really make sense, or I don't care because it's symmetrical anyway. So here we go. X is equal to square root of 3. So, I'm sorry, I read it out loud, which is good, but I didn't actually show you where I was getting any of that information. That's the question that I'm working on. I'm going to be lazy. I'm not going to go back and do 28 minutes of video. So my apologies for that. So it says a rectangle is inscribed with its base on the x-axis and its upper corners on the parabola. Y is equal to 9 minus x squared. What are the dimensions of such a rectangle with the greatest possible area? All right, so that's why I drew that parabola, and then we were trying to stuff some rectangles underneath of it. Sorry that you didn't have anything other than a verbal context for what I was doing there. All right, so what do we want to do with that? Technically, that is the x value where we have a critical number. Again, I am going to decide this time to do a first derivative test. I could do it. Do you know what? I'm going to do a second derivative test because this is a super nice, tidy function. And so it basically just gives me negative 12x as my second derivative there, which means if I were to test the second derivative at this value right here, we could tell whether it was concave up or concave down. And if it's critical number and it is concave down, then it's a max. And if it's critical number and it's concave up, then it's a min. And in this case, it's negative because it would be negative 12 times root 3. So negative second derivative. That means it's concave down, which means that this is a local max. So local max at x is equal to positive root 3. So that's good because we're looking for the greatest possible area. Now, the only thing would be, what would the boundary conditions look like? Because x values being equal to root 3, I said that 0 was going to be kind of a limit because I don't care about the reflection thing. I don't think that's going to be too relevant. But on the other side, we would also have a limit, because if my x was bigger than 3, then I would be like outside of the parabola, and that doesn't make any sense either. So I need to make sure that things are within the 0 to 3, which they are, but I also need to make sure that 0 and 3 don't give me boundary conditions that are going to actually have bigger dimensions. From a visual point of view, if you have 0x, it's just basically a thin line that goes to the top. That's going to be 0 area, which is a minimum, I guess, but not a maximum, not a greatest. If I go all the way out to the edge, then I can't go up any, so it's basically a flat box. And I do not, in that case, get any area either. So my boundary conditions, if I were to do basically what is a at 0, well, I get 0. What is a at 3? Well, I'd also get 0. Now, I did that visually, but we could test the actual equation as well. So if I test this equation and say, what happens when I put a 0 in there? Well, I get a 0. What happens when I put a positive 3 in there? Well, I get a 0 too. So those are both true like that. And this, if I wanted to know what my area was that is going to be the greatest, then I would just put it back in there. So it would be 2 root 3 2 root 3 times 9 minus 3, so 6. 2 root 3 times 6 would be 12 root 3, I guess. Oh, don't be silly. 12 root 3 in terms of the area. And so I'm going to go ahead and test this graphically. And sorry for leaving it on the last graph there for so long. So main scene, smart graph. I'm a little bit thrown off now. iPad graph. All right, so this one, we would have the area function, which we said was 2x times 9 minus x squared. All right, so now we also have an idea of what kind of numbers we're looking at here, because we only care about numbers between 0 and 3 for the x. So I'm just going to put -1 to 4. And then for my y values, I know that it was 12 root 3. So 12 root 3 would be kind of like 30-ish maybe. So I'm going to go just -2 to 30. All right, so this is our function that we're looking at. It's part of a cubic, so you can see the rest of it there, but we only care about the part between here and here. So that looks like those were definitely no areas, those are mins. This looks like it is our maximum there, and it occurs at root 3. I mean, I could put the exact values here. So square root 3, comma, 12 square root 3. And so we would see that the maximum that we found does occur at that same spot. We add the exact values. Desmos puts it pretty close, but it's not using exact values in that particular example. So that's good. We did a good job. And I think since we're already cooking close to 40 minutes, I do have more examples, but we can do those a little bit later.